that in a couple of minutes or whenever you're ready, you can go ahead and get started. If you want, we can wait until 10 sharp.
I would wait until 10 sharp.
Yeah.
You know, I mean, I just came from teaching. I just rushed here, and I imagine that there could be other people.
Yeah.
In the
Absolutely.
same situation.
I mean, on the other side of the problem, they have to rush to teaching.
Okay.
A little bit before the very end. So.
Okay, no problem.
Yeah.
No problem. So let's wait a couple of more minutes and then we start.
That's good. All right, the broadcast is on.
Perfect. Shogun, I need to talk to you one of these days.
Okay, sure.
So don't get surprised if you receive an email.
Okay.
Yeah, about some stuff. Okay.
Yeah,
so
now it's easy. We can through the Zoom.
yeah. Now it's much easier. I agree. I think now is sharp. So Joaquin, if you think we can start, I will. Joaquin? Some stuff.
Someone needs to mute the broadcast. I don't know who it is.
Now it's easy. We can through the Zoom.
Yeah. Now it's much easier. I agree.
One second. Okay, that was me. All right.
Should I start?
Yes, let's go ahead.
Okay, so great. So thank you. So good day and very welcome to this Quantum Many-Body Days. This is supposed to be a series of exciting talks about frontiers research in quantum many-body theory. My name is Gerardo Ortiz, and I am the chair of the International Advisory Committee of this international conference series called Recent Progress in Many-Body Theories. And let me tell you a little bit about why we are having these Quantum Many-Body Days today and during the month of September. So initially, we were going to have our 21st international conference in Chapel Hill in North Carolina in September of 2021. And because of the pandemic, this has been postponed to September 2022. But we thought that to keep excitement and to keep the community connected, it was a great idea to excite the audience with a series of frontier talks given by, very well-known people in the field. And these are all frontiers topics that we would like, to see reflected in the conference in September 2022. So we hope that many of the people that are here will participate in North Carolina. So before we start the series, I would like to, the series of talk with Xiaogang, I would like to tell you a little bit about the series itself. What is the series Recent Progress in Many-Body Theory? So this is a series that has been out there for a long time. And essentially is if I have to summarize the topics that are treated in those series, they go, generically on frontiers, many-body techniques of any kind. Okay, field theoretic, numeric, you name it. Okay, algebraic, whatever you want. Okay, plus emergent phenomena and organizing principles that result from many-body interactions, and also about the quantum control and the novel functionalities that you can get because of that. Now, this is a widely based international and multidisciplinary series, and I would like to tell you a little about the history. Indeed, this picture, I think, is a very interesting picture because it shows the prehistory of this series. That started indeed after the excitement in the 70s about applying these quantum many-body techniques to almost everything, to high energy, to condensed matter physics, and to, in particular, nuclear physics, okay? And this particular picture indeed is in Urbana-Champaign, okay, in 1977, immediately a few months after, indeed, the person that is highlighted here, that is, a key character in this series, is Eugene Finberg. Okay, we can see other faces here. Okay, I invite you to look at this picture and try to guess who are the others in the audience. Of course, there is Hans Bethe. It's very easy to pinpoint, but there are many other famous faces here. But Eugene Finberg played a very important role, and indeed, in this series, and indeed, the series started in 1978. So almost immediately this prehistory started in Italy. And indeed, the one that was supposed to be this year was going to be the 21st of the meetings. And as you can see, almost expands all continents. I mean, we would like to get even Africa. We don't have Africa, okay, so far, but we would like to get also Africa. Indeed, just to put in context, I mean, Solvay Conference, which started in 1911, they have 27, okay, conference. So 21st, a meeting is nothing bad and, something to feel proud about. So what are the topics that are included in this series? So essentially, it's a broad range of topics that go from complex systems, computational many-body methods, to quantum information and computation, strongly correlated systems, and always there is a session about new frontiers, because there could be ideas, okay, that are emerging at that particular time. Indeed, I remember many of these new frontiers, things about topological matter. That was a new frontier many years back, okay, and that was presented in one of these meetings. But the key highlight of this series, indeed, is the Eugene Finberg Memorial Medal. That is essentially honoring Eugene Finberg, that has been someone that has been an example for many generations and had made contributions, to quantum many-body physics, in particular in nuclear physics, that were extremely important. And this Eugene Finberg Memorial Medal essentially is given to a distinguished scientist working in many-body physics that has established, has essentially published or established, a significant contribution to advance the field of many-body physics, okay? As you can see, there are many well-known people here. And indeed, some of these medals, in particular, the case of Tony Leggett and the case of Walter Kohn, they were given before the Nobel Prize, okay? So you have Nozier, you have, Gordon Benn, you have many famous people. I mean, I'm not going to name all of them, but this is a highlight of the meeting. So in every single meeting, there is a scientist that is recognized because of contribution. Now, more recently, indeed, the International Advisory Committee thought that, I mean, it's important also to recognize the achievement of young people. Okay, people that start making significant contributions at a young age. And indeed, I mean, we have not made almost any mistake here, okay, because these young physicists indeed have made outstanding contributions since then. I mean, before then and even, afterwards. And this award is given for young physicists that has published work that have made a significant contribution at the time. Okay, there are some rules. Okay, to quantum many-body theory. In particular, we have three of them, okay, that I highlighted here: Frank Verstraete, Xiaolian Shi, and Max Metlisky, that will be speakers in this series. So we are really very thankful about that. And we have our own Joaquin Ruth, that is the great organizer, not only of this series, but also of the next RMPV 21 conference series. With this, I would like to stop, and I will leave you with the more interesting stuff, that is the talk of Xiaogan and Xiaolian Shi. Okay, see you. Thank you.
Thank you, Gerardo, for those remarks. And we're very excited to have Xiaogan Wang today. I would like to briefly introduce him, although I think for this audience, especially for the condensed matter people, he hardly needs to be introduced, but I will still say a few remarks. Xiaogan Wen got his PhD from Princeton in 1987, and working with Ed Witting in the area of string theory. And then he switched to condensed matter and worked for some time with Bob Schrieffer, Frank Wilczek, and Tony Z. He eventually joined the MIT faculty in 1991, and eventually became the Cecil and Ida Green Professor of Physics at MIT, started in 2004, where he is now. Wen is also a distinguished Moore Scholar at Caltech, that's in 2006, and was also a distinguished research chair at the Perimeter Institute in 2009. And among other honors, he is the Sloan Foundation Fellow, an APS Fellow, and has received the APS Buckley Condensed Matter Prize, and more recently, the Dirac Medal of the ICTP, together with Subir Sakdev and Dam Son. Now, those are only a few of the honors, but I don't want to make you wait any longer. So without further ado, we're very happy to have Xiaogan Wang here today, who will tell us about emergent higher symmetry and topological order. So Xiaogan, if you want, please go ahead. You can share your screen and take it away.
Okay. Thank you very much. It's really a great honor to speak in this many-body series. And it's really have a very long history. I remember I'm reading this Finberg's book and very impressed by the techniques in the book. So today I'm going to talk about the topology order and the related phenomena of emergent symmetry and emergent higher symmetry. So we know that for a long time we thought that the all phase of quantum matter are described by Landau symmetry breaking, and we can use a group and order parameter to describe them. However, in early days, high-T superconductor, Anderson actually suggests that maybe a spin liquid would play a very important role to understand high-TC superconductivity. And but there is an issue how to characterize a spin liquid, because spin liquid by its name means a spin state without spin order. So it's defined by, it is not something we are familiar, but what we don't know what it is. So at that time, we are still thinking about the symmetry. So we find that maybe we can use a time reversal symmetry or parity symmetry breaking to characterize a spin liquid. And this led to the so-called Carroll spin liquid. But during that study, we also realized that there are several different chiral spin liquid which have same order parameter, same symmetry breaking, but they're still different. So therefore, there's still a puzzling, how to describe those different chiral spin liquid which have same order parameter, same symmetry breaking. And this is a little bit slow. So in this in the quantum Hall states, we have a similar problem. We have several different quantum Hall states described as a plateau, different Hall conduction plateau. But they all have the same U1 symmetry, and they do not break this U1 symmetry, and they don't have other symmetry like translation and etc. all broken by impurity, things like that. And so all those different quantum Hall states have the same symmetry and have same symmetry breaking pattern. So there's an issue, what distinguishes them. So this relates to the concept topology order. That is, there's something beyond the symmetry breaking which can describe this quantum matter. But what is a topology order? So very roughly speaking, we have three kinds of quantum matter. The matter at 0 temperature. The one which have a energy gap means a low energy excitation. So therefore, at low energy, they're nothing. So it's kind of trivial. And the second class will be there's a little bit of low energy excitation, like a superfluid. There's a few low energy excitation. And we say that's interesting. And the metal have a lot of low energy excitation. And we say that's a messy. So from this very simple point of view, we say that topology order is kind of trivial because there's nothing at low energy. So it's kind of trivial thing. But however, it turns out that this so-called trivial topology order actually is kind of non-trivial. They have a lot of internal, very rich internal structure. But the issue is how to see this internal, the universal property of this structure. Okay, because the wave function of many particles is very complicated. We don't see anything from this wave function of 10 to the 20 variables. Okay, and here the idea is that we can put this wave function on the space with a different topology, like on the sphere and on the torus and etc. Okay, and so therefore, so then we can measure what we can measure ground state degeneracy. Okay, then different ground state degeneracy, and they may depend on topology of space, and this reflect the different internal structure and a different order. Okay, and so in today's talk, I will not talk about chiral spin liquid, which indeed have a topology order as defined from this ground state degeneracy. And but we'll talk about the another topology order, but which do not break time reversal and parity symmetry. And this topology order are really can arise from frustrated spin liquid with the frustration, and following Anderson's idea, maybe those spin liquid may be formed by the spin singlet dimers, and this dimer may fluctuate, and we get this dimer liquid or string liquid. Okay, and however, there's a more convenient way to see this dimer liquid or spin liquid. Actually, is to view it as a string liquid. It's a string liquid. The reason is that whenever we have a dimer pattern like this, we have we take one dimer pattern as a reference, and every other dimer pattern compared to reference, we can just lay on top of each other. Do you find this the difference of two dimer pattern actually is a string, and this unpaired spin actually is the end of a string. So this is so therefore the fluctuation of a dimer pattern can be viewed as a fluctuation of a strings, and this string is a much more powerful, a much better picture. And so this is how we view topology order. So in the sense, the topology order is nothing but a superposition of all kinds of a string configuration. In particular, it's a closed string configurations. Okay, and so this is one way to look at the topology order. And in particular, for this kind of Z2 spin liquid or this string liquid, and we can have a topological extension. That is one of the character of a topological order. For example, if all the strings are loops, then there's ground states. The equal weight superposition of a loop is a ground states. But however, if we have an open string, then string n would represent the extension. So this kind of superposition of string n, so this a straight one and the hooked one, is a very simple end of string. It turns out to be a boson because it's involved unpaired spin. So it's a spin 1/2 boson. So that's one of the topological extension in this string liquid. Okay. Actually, there's another kind of topological extension we call the M. We call the flux, and which is a little bit more subtle. That is we just pick a point in the space. And if the wave function, then the amplitude of the wave function depends on how many times the string wrap around this point. If the string wrapped on this point is the number is even, then the amplitude is plus. If a number of a string wrapped on this point is odd, the amplitude is minus. So really say that even minus odd. And this also, because we multiply the wave function, so this also represents a particular topological extension. We call the flux-like extension, which is spin 0 boson because we have no string end. String just all closed. And then the combination of these two the two extensions actually modify this sign. You can see the straight end and the hooked end, they differ by a loop around this point. And so a single loop around this point have a minus sign means we have this flux extension. So if a change sign here, this is like a bound state between E and M. Okay, that's another topological extension. Then something pretty magical happened here. This kind of string n with a minus sign, the straight minus hooked, actually it's a fermion. So the strange thing like this can happen in the topology order. That is, we can have a quasi-particle even with fermionic statistics, although our starting point and spin are all bosonic. So we have 3 types of non-trivial topological extension, and 1 type of trivial extension. It's just nothing. Okay. So there are total 4 types of excitation, and so this is a string liquid. And today we want to motivate our next discussion. We want to consider the following question. So let's assume this flux excitation have a low energy and may condense and may drive phase transition. And so we can ask what kind of phase this M condensation can induce. Or we can have another situation where M and F excitation very high energy, but the E have very low energy. But this E is a boson carrier spin 1/2, and they may condense. So what kind of state this E condensation can induce? Or we can have M and E have very high energy, but F have low energy, and F condensation may induce some phase, and what phase they can induce. And so that is a physical question we want to address. It turns out that one of very good way to addressing those questions is to study emergent symmetry. Actually, for different scenario I just mentioned, there is a different emergent symmetry. But however, those emergent symmetry are not ordinary symmetry. They are so-called higher symmetry. And using higher symmetry as a guide, we can understand the physical question I just mentioned. Okay. So what is a higher symmetry? So let's study this topological model introduced by KTF, which actually is an exact solid model which realizes it's a string liquid or this Z2 topological order. Okay, and so here we consider a topological model on the Kagerman lattice, which is formed by link of a honeycomb lattice. Okay, And we have a term of Q term. A Q term, which actually is a product of the term which is around this three sides around the vertex. Okay, and we have this F term, which is a product of a poly X operator around this 6 spin around this hexagon. Okay, and these two operators turn out to commute. So this really commuting projector model. So they're totally soluble. The topological extension in this model is very simple because there's a particular eigenstate, which is both Q and F are equal to 1. That's a ground state because those coefficients are negative. And then if I change it from 1 to +1 of a Q operator, that's an extension. So that means a certain vertex get a higher energy. If you change F from 1 to -1, then that means certain plaquette have a higher energy. So that has another type of extension. It turns out that the flipping of a Q is an E-type extension, and the flipping of a plaquette is an M-type extension. And those are topological extension because those extensions cannot be created alone, unlike a spin flip. We can flip a single spin. But for a particular reason, we cannot flip a single vertex or flip a single plaquette. We have to flip them in pairs because the flipping operator actually is a string operator. To flip those plaquettes, say for example, to flip the vertex, for example, let's consider this red line. This red line is a string operator, which is a product of poly X operator along these strings. And from here, we can see that they flip. When you apply this operator, they flip the Q operator at this vertex and flip a Q operator at this vertex. So the end of a string is a flip, but the middle of a string is not flipped, so it costs no energy. So you can see that this string operator created a pair of E particle. We can never create a single E particle. They always create in pair. So that's the character. Those are topological extension. They cannot be created alone. Similarly, on the dual lattice, we can have this a dual string, which is connecting the center of a plaquette. That's a dual string, and which the product of poly Z operator on the dual string give us this M string operator. And similarly, applying M string operator, flipping the two plaquette near end of string, does create a pair of M extension. And from here, we can see that this string operator have a property that for the closest string, they commute with Hamiltonian. So that means the string body don't cost any energy. But open string do not commute. The string end of open string under commute. And so they create energy. So that is the idea to using string picture to understand the extension of a toric code model. Okay. But actually, this string picture is nothing, but actually it's a picture of a higher symmetry. Okay. So let's first describe a zero symmetry. That's an ordinary global symmetry called the zero symmetry. The zero symmetry is generated by the symmetry action, which act on every side. So like this product of Z operator on every side is a generate a Z2 symmetry. Actually, the toric code model have this Z2 symmetry because this Hamiltonian commute with this symmetry generation operator. So that is a symmetry. Now we just mentioned that we have a closed string operator which commute with Hamiltonian. Okay. So we can view those closed string operator also generate a symmetry. Okay. And this is nothing but a higher symmetry. So this M-type closed string operator commute with Hamiltonian. We generated this, the E-type closed string operator. And we generate this Z2E symmetry. And this M-type string operator generated this Z2M symmetry. And they are called one symmetry because those closed string have a codimension 1. So the symmetry are codimension 1, not the dimension of string. We have 2-dimensional space. String have a codimension 1. So those are called the one symmetry. Okay. So that's it. So this is so topological model is very special. Not only to have this global Z2 symmetry, but have this very special Z2 one symmetry because the closed string operator commute with a Hamiltonian. So that is a very simple way to define a higher symmetry. So actually, this higher symmetry has been studied quite extensively before. That is especially in quantum information. So they are viewed as a logical operator because it's a Tor code. The degenerate ground state is like a code, but the logical operator are those string operators. Okay, and this Tor code from string picture have this string condensation. So this is because string condensation, we also study this string operator very extensively. And in particular, in this paper, maybe almost 15 years ago, and it's emphasized that this topology order and this string operator, which is called a low-dimensional gauge symmetry, have very close connection, and which we'll try to explain that later. And in this paper in 2014, and it was emphasized that this kind of a higher symmetry or higher form symmetry should be viewed as a generalization of a global symmetry, okay, and like a zero symmetry. And there's many ideas, all kind of idea about the global symmetry actually equally apply to this higher symmetry. So this really so they have like a very systematic point of view, a very general point of view of this matter. So that's really a launch this higher symmetry into a very active field. And here I just want to mention that the higher form symmetry and the higher symmetry is almost same, but there's a slight difference. The higher form symmetry can be viewed as a low energy effective symmetry of a higher symmetry. So there's a higher symmetry in low energy subspace became a higher form symmetry. So there's a slightly difference. So therefore, the higher form symmetry is a low energy symmetry. So actually, it's a symmetry of a field theory. Field theory is low energy effective field theory. So therefore, higher form symmetry is introduced in field theory. So it's a low energy effective theory. But the higher symmetry really is introduced in a lattice. And so therefore, it's a lattice high energy symmetry. It's really symmetry about the lattice Hamiltonian. But the higher form symmetry is a low energy effective or emergent symmetry of a field theory. So there's some slight difference here. Okay. So so here I just mentioned that if you view the Tor code model as a model with a higher symmetry or as a one symmetry, then actually one can understand the topology order as a symmetry breaking of the spontaneous symmetry breaking of a higher symmetry. So first, let me just explain the spontaneous symmetry breaking of a zero symmetry and its relation with the ground state degeneracy. It's well known that when you have a transverse Ising model, if you break the zero symmetry, and we have a degenerate ground state, all spin up and all spin down, they are degenerate ground states. But mathematically, using the degenerate ground state, we can define what is a spontaneous zero symmetry breaking. It's by examining how the symmetry transformation act on the ground state. So this spin flip is a symmetry transformation. And when the symmetry transformation act on the ground state, we find the symmetry transformation act non-trivial on the ground state. It's changing one ground state all spin up to another ground state all spin down. Or we can have a superposition to ground state, plus or minus. And for plus ground state, this symmetry transformation have a positive eigenvalue. For negative ground state, it have a negative eigenvalue. So the point is that this degenerate grounded subspace form a non-trivial representation of a symmetry transformation. The symmetry transformation is not proportional to identity operator in the degenerate grounded subspace, and that's a key point on first. Whenever this happens, whenever symmetry transformation is not proportional to identity operator in a degenerate grounded subspace, ground state subspace, there's a spontaneous symmetry breaking. Okay, so using this definition, we can say that actually the ground state degeneracy for the topological model on the torus have a spontaneous breaking of a higher symmetry. And so here we consider the higher symmetry transformation for the loop, which go all the way around the torus. So here, this square actually means torus. So this blue line is a type E string operator wrap around this torus. And this this blue line here. And this red line is a type M string operator wrap around the torus, but in the opposite direction, in the perpendicular direction. Okay. And remember that E is a product of Z, M is a product of X, and X and Z anti-commute. So it turns out that these two string operator, they have one intersection, so they anti-commute. Okay. So therefore, but however, the Hamiltonian commute with those two generator, but these two generator anti-commute. So therefore, the ground state subspace form a algebra representation of this algebra, which have only two-dimensional representation. Okay, so therefore they must be degenerate, at least twofold degenerate. It turns out we have another algebra, which is the E operator is a vertical and M is horizontal, and so this ground state also form a representation of this second algebra. This also anti-commute. So there's a total, we have fourfold ground state degeneracy. Okay. So therefore, this fourfold degenerate ground state is what Tor code is for. That's a representing topology order in the Tor code model. But clearly from definition, we can see that this higher symmetry transformation do not act as an identity operator in the ground state subspace. So therefore, this fourfold degenerate ground state can be viewed as a spontaneous breaking of a higher symmetry. Okay, so this is this is the picture. That is actually the topology order and the corresponding ground state degeneracy can be viewed as a spontaneous broken of a one symmetry. So that's just a kind of unify this topology order and the symmetry breaking picture. It's kind of very interesting because the topology order at the beginning is introduced as a new kind of order beyond the symmetry breaking. But now, after so many years, we find it can also be understood using symmetry breaking picture. But it's a higher symmetry, a spontaneous breaking of a higher symmetry. However, there's something quite different here. Because when I say topology order, we really say that something robust against any perturbation. The perturbation can break any symmetry. But however, from this picture of understanding topology order, we say that the topology order coming from higher symmetry breaking, a spontaneous breaking of a higher symmetry. That sounds like if you don't have a symmetry, higher symmetry, then we don't have a topology order. But on the other hand, the topology order is defined for the system even without any symmetry. So there's some contradiction here. It sounds very puzzling. Okay. And so here actually, that's something which the one symmetry, a zero symmetry, and a higher symmetry are quite different. And so we know that spontaneous zero symmetry breaking led to this a degenerate ground state. However, if we explicitly, sorry, there's some spelling. If you explicitly break this zero symmetry, the ground state degeneracy will be destroyed. We will leave the ground state degeneracy. And so therefore, at the low energy, we don't have a emergent zero symmetry. But in this aspect, the zero symmetry and the one higher symmetry is very different. Because as we see that spontaneous breaking of a higher symmetry also led to degenerate ground state. But here, that's all happen only on space with non-trivial topology, like on a torus. The degenerate ground state do not appear on the sphere. Okay. However, the explicit breaking of the higher symmetry does not lift the ground state degeneracy. That is the difference. So therefore, even we explicitly break higher symmetry at the lattice level, the ground degeneracy remains. That sounds like the higher symmetry is still there at the low energy. So we have an emergent low energy higher symmetry. And that is a difference between this zero symmetry and higher symmetry. And actually, we can understand this from our algebra argument of the degenerate ground state, because this string, E string, and this vertical M string, their algebra gave us degenerate ground state. And you can imagine we can add some impurities away from these two strings. When you add impurity away from these two strings, the Hamiltonian with impurity still commute with this particular E string and this particular M string, and the Hamiltonian still commute with that, and these two strings still do not commute. So they're still guaranteed to have ground degeneracy. So it's amazingly that those impurities away from this particular string cannot lift the degeneracy. Okay, and so this is what is so special about the higher symmetry. Adding impurities do not lift the degeneracy. We still have a degeneracy. So therefore, the degeneracy is topologically robust. Or another way we can say that the emergent low energy symmetry is topologically robust, even when you break the lattice symmetry explicitly. So therefore, we can have a spontaneous breaking of emergent higher symmetry, and that gave us a topology order, this emergent topology order, which is robust against any perturbation. Okay, so this is what we try to see here. That is the torical model plus perturbation actually do not have this Z2 there should be not here. they do not have this Z2 symmetry, and but they still have degenerate ground states, and so this degenerate ground state can be viewed as coming from this emergent Z2 symmetry. Okay. Yeah. So so here, what we just talked about is that we emphasize that this emergent higher symmetry. Okay. What we talk about is if our lattice model have a symmetry, then the spontaneous breaking of a higher symmetry can give rise to topology order. Okay, and this phenomenon is even valid if we break the symmetry explicitly at a lattice scale, because we have an emergent higher symmetry. And we have a similar phenomenon that is in this paper that I'm pointing out that this gapless U1 gauge boson can be viewed as a spontaneous breaking of U1 symmetry. Now we have a continuous higher symmetry, U1 symmetry. Okay, and then actually here we have a similar thing that even at the lattice scale, if you add a perturbation to break this U1 symmetry explicitly, and we still have gapless gauge bosons. The gapless gauge boson is something topological. Even if you break U1 symmetry explicitly, we cannot lift energy gap for the gapless gauge boson. Okay, and the reason is similar, because we can add a perturbation to explicitly break U1 symmetry at the lattice scale, but for some reason, this emergent U1 symmetry at the low energy remain to be exact, remain to be unbroken. Then the spontaneous broken of this emergent U1 symmetry will lead to this gapless gauge boson. And so therefore we have a very interesting phenomenon, very similar to gapless Gaussian mode. We know that the spontaneous broken of continuous zero symmetry would lead to gapless Gaussian mode. And similarly, spontaneous broken of a continuous one symmetry will lead to gapless gauge boson. But for the second phenomenon, it's topological. Even we add a perturbation to break U1 one symmetry explicitly on the lattice, the emergent U1 one symmetry remain unbroken, and we still remain to have this gapless U1 gauge boson. So this is a similar phenomenon we just mentioned, that this spontaneous broken of a discrete higher symmetry is robust against perturbation, which breaks symmetry explicitly. And so this also happened for the one symmetry. Okay. So last, let me just quickly explain this higher symmetry in some more details, and then come back to the question I raised at the beginning. When this E excitation, M excitation condense, what kind of phase they can induce? Okay. To understand this higher symmetry and emergent higher symmetry in more detail, so let's try to understand what is the charge of the higher symmetry. You know, for the zero symmetry, for the global symmetry, we have a charge operator. So what is charge operator? Okay, and it's very simple. For the global symmetry or for the zero symmetry, our symmetry acts on the whole space. And the charged operator is the operator which transform non-trivially under symmetry transformation. Okay. And here I would introduce so-called neutral charge operator, which is a pair of a charge operator. As a whole, they transform trivially. So there's neutral, there's no charge. But however, they formed by two charged operators. So each part have a charge. But the two charge operators together give us something which are neutral. Yeah, that's a neutral charge operator. Why introduce this operator? So will be clear in a moment. For the U1 one symmetry, which are generated by this loop operator, which is poly X operator, the product around a loop. This S1 is a loop. So, and in this case, this is so-called neutral charge operator. So the correspondence or generalization of this ZIVJ actually is an operator which is a product of Z operator around the loop. Okay. These are neutral charge operator because they do not change. These two, they do not change under this one symmetry generated by this loop operator of a poly X operator. So therefore, they are really carry no one charge. They're neutral operator because of this. And the charged operator, what is charge operator? The charge operator is a part of a loop. Okay, it's very much like this. The neutral operator is a 2 point. The charge operator is 1 point, which is part of a 2 point. Well, that sounds strange. The reason is a 2 point actually is S0. It's a 0-dimensional loop. So S0 is a 0 dimension, but it's 2 point. The part of a 0-dimensional loop is 1 point. And this picture works. For in 1 dimension, a loop is S1 just a circle. The part of S1 is part of a circle, it's an open string. So therefore, the charged operator is a product of Z operator along the open string. So that is the charged operator for the higher symmetry. And then we can measure the charge carried by charge operator, because for the charge operator, for this open string operator, this and the transformation of this one symmetry, they may change in sign, plus minus sign, just like a Z2 symmetry, they may change in sign. And the things that this black circle is a one symmetry transformation. This blue one is a charged one charge. Okay, if they don't intersect, okay, then they commute. So you don't measure charge. However, if these two strings intersect, then you measure charge. There's a -1. So therefore, so that's why this open string operator actually is a charge of this one symmetry. Okay, so this became the language we are going to use. Okay, and so this is but there's another way. Okay, yeah. So we can also detect the charge in a neutral charge operator. As I mentioned that for this neutral charge operator, we have a hard time to detect the charge because they commute with the symmetry transformation. But actually, there's a way to even detect a charge within this neutral charge operator, and that is this the patch symmetry transformation. For example, for the zero symmetry, what is the patch symmetry operator? That is we only perform a symmetry transformation not on the whole space, but only in a patch. Okay. In this case, we see that for this patch symmetry transformation, and we can, if this patch symmetry overlap with one of a point of a 2 point, we can detect. We have a minus sign. We can detect the charge. However, if both points are within the patch, we cannot detect the charge. If one point within the patch can detect the charge. Actually, we can also do this for patch symmetry operator. It's a symmetry transformation on the open string, not on the loop. So that's a patch symmetry operator for one symmetry. We have a symmetry transformation on the open string, not on the loop. Here I draw it incorrectly, actually. Then the neutral charge operator actually is a loop. You know, it's kind of like loop like this. So we can have a loop. However, but for the patch operator, for the patch symmetry operator, it's open string. Then if this open string symmetry transformation intersect with our neutral charge operator, which is a loop like this, then we have a minus sign. We can detect a charge. Okay. So to summarize that, we see that for this Z2-1 symmetry, we call the Z2-E1 symmetry generated by this E string. This E string generate this Z2-E1 symmetry. Their patch symmetry operator is an open string operator. Okay. And its charged operator is also open string operator. But this open string operator happens to be the M string. It's a product of Z. So very nice pattern. So the string operator we introduced before, one of them is a patch symmetry transformation operator, and the other happen to be the charged operator. But however, for the Z2-M symmetry generated by this M string, their patch symmetry operator is M string, but the charge is a E string. Well, it's very interesting. This symmetry transformation patch operator and the charge operator are very similar. They both a string operator, they both open string operator, and they can exchange depending on what you call symmetry, what you call charge. So this is a quite interesting observation. And so higher symmetry, the charged operator and the symmetry transformation operator get mixed up. Okay. And we can have the bound state. We can have a composition of the Z2 symmetry. So this string operator times that string operator generate this F string, Z2-F symmetry. Their patch operator is F string operator, whose endpoint is a fermion. Okay. So from here we see that it looks like this Z2-1 symmetry, Z2-E1 symmetry, and Z2-M1 symmetry, they are due to each other. Their patch symmetry operator and the charge operator get exchanged. Okay. So using this kind of language, and so let me skip that. So let's understand this the symmetry breaking in the Z2 Tower code model or in Z2 topology order. As we mentioned that the Tower code model have an exact Z2-E1 symmetry and Z2-M1 symmetry. So what that means? That means this Hamiltonian of this Tower code model do not contain charged operator. So those open string operator is not allowed in the Hamiltonian, because those operator, the charge operator, when you include that in the Hamiltonian, they break the symmetry. So Hamiltonian do not include those charge operator. But what are those charge operator? Actually, those charge operator actually is a hopping operator of E particle and M particle, like this M string, open string operator, charge operator, actually is a hopping of M particle. And this E open string operator is a hopping of E particle. Okay. So this is very good. This is a very important point. The Tor-code model have a exact one symmetry, really, because this M particle, E particle, F particle, they are immobile. They cannot hop. The reason that they cannot hop is the reason that they have exact symmetry. However, if you add this kind of a short string operator like a Z operator or X operator, they are correspond to a short string operator. That's induce hopping of those topological excitation, and that those kind of hopping term explicitly break this one symmetry. Okay. Okay. So from here, we can introduce a notion of a transformation anions and a notion of a mobile anions. Okay. And the transformation anion basically is that we know that the one symmetry are generated by string operator, and the other string correspond to anions, and those anions are called the transformation anions. And the mobile anion are those anions which can move. Okay. And so it turns out that we can understand whether symmetry broke or not by this picture. If the transformation anion and the mobile anion have a trivial mutual statistics, then that means we have this kind of higher symmetry described by this transformation anion. Okay. For example, for the Tor-code model, every anion is immobile. So therefore, every anion can be transformation anion. So therefore, all the anion can correspond to the higher symmetry. However, if some anion became mobile, then the anion which have a non-trivial mutual statistics of this mobile anion cannot be one symmetry. That one symmetry is broken. Okay. And from this picture, we can really understand this emergent symmetry, because mobile and immobile can be replaced by low energy and high energy. Mobile means that relevant, they participate dynamics like a low energy excitation. If some anion have very, very high energy, they don't just even appear, and we don't care whether they are mobile or not mobile. They just don't appear. So therefore, high energy anion is like immobile. And so therefore, we can state our previous result in the following way: that we can have low energy emergent one symmetry described by this transformation anions. And if those transformation anions have a trivial mutual statistics with all low energy anion, so that means if you have low energy anion, have a high energy anion, some anion have very high energy, then then we may have a non-trivial emergent symmetry, because those high energy anion do not participate. The low energy anion may have a trivial mutual statistics with some set of anion, and this set of anion would give us emergent one symmetry. Okay, and then let's consider one example. For example, we have for the Z2 topology order, we have a three kind of excitation. We have this E, M, and F. Let's assume the energy gap of M excitation very low, but the E and F is very high. Okay. Then below this, so therefore low energy anion is this M particle is a low energy anion. Okay. Then we say what kind of anion have a trivial mutual statistics with low energy anion? The answer is M anion. The E anion and F anion have a non-trivial mutual statistics with low energy anion, so they don't count. But M anion have a trivial mutual statistics with itself. So therefore, if M anion have low energy, E anion and F anion have high energy, then we have an emergent Z2M symmetry. I think this is a key point. For any topological order, whenever we have a separation energy scale for certain anions, then we have emergent symmetry. We can determine which symmetry are emergent by say which symmetry have a trivial, which anion have a trivial mutual statistics with those low energy anions. And that's really the key point of this talk. And this is very useful because this emergent symmetry exists as long as all energy scale below this energy gap of E and F. They appear even above energy of M particle. So therefore, we can consider the condensation of M particle. We can reduce the gap of M particle to negative, make M particle condense. In the whole process, we have this one symmetry. So therefore, this phase transition is controlled by this emergent Z2 or one symmetry. So therefore, this M condensation can induce phase transition, can induce a critical point. All those phase transition, all these critical point, they all have this one symmetry. Okay, and similarly, we have a similar picture. We can have another symmetry called the Z2F symmetry. That's if F particle have low energy, then E and M particle. Then at the low energy, you have emergent Z2F symmetry. Okay, and this F particle condense can have fermion condensation, can have transition, and all these process are controlled by this Z2F1 symmetry. But however, this Z2F1 symmetry is anomalous, and so therefore it have this anomalous. So they have some constraint. For example, this fermionic condensed states can never be a trivial product state. Okay, so maybe let me stop here. So that is my point line. My bottom line is that for the topology order, whenever we have an energy scale separation, we have low energy topologization, and from there we can determine the emergent symmetry. And the dynamics of those low energy topologization are all controlled by this emergent symmetry. You can start a phase transition critical point, assuming we have those emergent symmetry or higher symmetry. I think this became very powerful tool to understand the possible phase and the dynamics of topological matter. Thank you very much.
Thank you very much, Yagan, for a nice talk. So, of course, I mean, now we are open to questions. I mean, you can ask the question raising your hand or in the chat. So meanwhile, I can ask you a question while people are thinking about questions. I can ask the obvious general question. I mean, that is, I understand your way of, if you want, detecting the immersion of this high dimensional symmetry.
Yeah.
But the real question as a physicist or an experimentalist would be, how is that I experimentally can design some sort of witness or, you know, some sort of measurement or something that can detect these phases? I mean, that's the obvious question, of course, I know. Yeah. But have you thought about that?
Yes, I thought about that, but okay, let me consider one thing. Okay, we can see that what I'm going to discuss a little bit theoretical, not quite experimental, but it's measurable, and so who knows? Some days experiment can really measure those. Okay, what I try to say for the for the zero symmetry, for the spontaneous zero symmetry breaking, how do we detect that? I think numerically, we detect off-diagonal long-range order. So we measure off-diagonal long-range order is a way to detect spontaneous zero symmetry breaking. And so we can ask how to detect spontaneous breaking of a higher symmetry. Do we have something order parameter long range order to do that? And here I want to emphasize that the so-called off-diagonal long range order is nothing but an average of a so-called neutral charge operator. That's why I introduced this neutral charge operator. Its average neutral charge operator is non-zero in the ground state, means off-diagonal long range order. Because this ij can be very far away, so neutral charge operator can be very large. But even for large neutral charge operator, they have a non-zero average. So that's the signature of off-diagonal long range order of spontaneous zero symmetry breaking. And once you understand the zero symmetry breaking in this way, we can generalize this to higher symmetry. That is the average, ground state average of a neutral charge operator of a higher symmetry. It's an analog of an off-diagonal long range order of the higher symmetry. Okay. And this, remember, this neutral charge operator is a closed string operator, but the string can be very large. So even for very large string, we have a non-zero average. Okay, and so therefore this non-zero average, numerically you can use this to detect a spontaneous breaking of a higher symmetry. This average ground state average of this neutral charge operator. Yeah. And certainly, if you can, but because those are extensive operators, so therefore to design expanded probe for that is difficult. And but if you have a lot of quantum control, we probably can do that. Actually, this matters for the quantum information. To use a logical operator, we need this kind of thing, quantum control, to use a logical operator. If you can control logical operator, those are neutral charge operators are really logical operators. It can control that, measure that. That's really a measure of diagonal long range order for this spontaneous higher symmetry breaking. Yeah. So that's one example. There's other things. Yeah.
Thank you, Shagan. So is there any further question out there? I am seeing that the audience is very silent. So any other question there? I am not seeing. No, I mean, you know, this is one of the big questions that are, you know, popping up right now. Because, you know, big facilities and, you know, and labs, I mean, they are interested in, you know.
So I think originally I thought, lattice higher symmetry probably is not important in condensed matter because it's hard to have a Hamiltonian which commute with all loop operator. That seems difficult. Or maybe sometimes people in cold atoms can really design such system. Okay. But however, I think people do think maybe the topological order or this topological phase matter probably can be realized, and we can find the material in quantum Hall states. That's not probably, so we're sure. In quantum Hall state, we do realize this topological order. But in spin liquid, we're still waiting for the good news. And here I want to emphasize that in those topological matter, as long as you have this energy scale separation, or if you want to study the condensation of a particular topological excitation, that means those topological excitations have low energy, but others have high energy. And those are precise situations we have a higher symmetry. And to study those kind of critical points, those kind of phenomena, assuming higher symmetry is a very powerful theoretical tool. Yeah, that's the main message. So whenever we have a topological phase matter, and when you study phase transition with topological phase matter, the higher symmetry will be very important tool because the critical point will have those higher symmetries. And so that's allow us to understand why topological phase transition can be special, can be interesting, because they have emergent higher symmetry, and their property probably can be determined by those emergent higher symmetry. I think this is a point I try to emphasize.
No, thank you. So I agree. I agree on that philosophy.
Yeah.
So more questions out there. So I have more questions, but I want to know, I don't know, I don't want to capitalize the whole thing. So I would like to thank Shogun again. Thank you very much for such a nice and illuminating talk. Okay, and I will contact you. I have some.
Yeah, thank you very much. Yeah, and thank you for organizing the series. Yeah, it's very
Thank you, Shogun, and thank you, everybody. So I remind you that our next talk is at 1 p.m. Eastern time, okay, and is by Xi, okay.
Yeah.
See you and see you
Bye-bye.
later. Bye-bye.